Hey, so I was working on some problems and I came across this one. And we were in the linear differential equations or first order differential equations. And this one just threw me for a loop. And I thought, man, that's a lot more involved than some of the stuff we did. It's got this kind of special technique of integrating where it doesn't quite fit what you would normally look at for integration. And that happened in Calc 2, but when I came across it, I thought this deserves its own video. So we're going to go through this example. I'm going to go quite slow on this one because it's so involved. There's lots of room for errors. And frankly, I made a couple errors myself when I did it the first time. So I wanted to give you the courtesy of giving this problem, walking through it with you, and just showing you exactly what takes place. So sometimes we get these difficult integrations or these integrations that don't quite fit. I want to look at that with you. So let's go through it together. Let's see if we can classify this as a first order differential equation that happens to be in that linear category. And let's work with it. So we're looking at this, we're going, wow, that's a differential equation, of course. We have an initial value problem. We've got an equation, first order differential, and we have y to the first power. So let's try to get this to look like how we really want our linear equations to look, with just that dy dx, and then we have this thing, this function of x's next to our y on one side, and then equals this function of x. So if you've watched the last video, that should make sense to you. If you haven't, you really should watch that. Right now, this is a great opportunity for us to kind of go step by step, see if you can do the step. That's why I'm going to be going slow, to see if you can work through it, and then seeing if we're on the same page. So is it a linear first order differential equation? Yes. Is it in the right form? No. You should probably try to put that in the right form right now. We want the dy dx to be by itself, function of x times y, and then equal sign, and then another function of x, no otherwise. So that means for us, we've got to divide by the x squared plus 1. We're going to do that. Divide all three terms by that x squared plus 1. And so we get that. That's the form that we want. So if that's familiar to you, that's fantastic. You know the proper form for solving these first order linear differential equations. Now, it looks fairly benign, like, yeah, okay, no problem. It's in the proper order. This thing is the function of x that we're looking for. So that right there is that p of x we're talking about. Remember, with linear first order differential equations, we're trying to find something to multiply by so that we can create this result of a product rule. If we can create the result of a product rule, we can write the product. If we know that that was what we have here is the result of a product rule, okay, well that's great. Then we can take an integral of both sides and solve for our function. So right now what we're going to be doing is we're going to be finding this thing to multiply by, this integrating factor that we're multiplying by, that's going to multiply every single term. It's going to create for us the result of a product rule. Then we're going to integrate, and that's all that we're going to do. So we're going to find the product, and then we're going to integrate both sides. In order to find that integrating factor, what we talked about last video was that we want it to repeat. So we want the derivative of this thing to repeat. The function and the derivative of the function need to have the same thing in it. That means we're going to have e to a function. Also, because it's the result of a product rule, the thing we're multiplying by here is going to be part of that product. So this is going to be the x part of that product. This has to be the derivative of the exponent of that exponential that we're going to multiply by. And that was in that last video. So our p of x is this whole entire thing. All right. No problem. That means that if we're going to find, if this is the derivative of some exponential function, the exponent of that exponential function, then rho of x would equal e to the f of x. Sure, rho of x, that e to the f of x is the only type of derivative that or only type of function we have, where when we take a derivative of it, we get the function back. So on our product rule, we want this piece to go here, and we want the derivative of this piece to be here. That's what we need. We need it to repeat. It's just going to be tacked on over on this right-hand side. It was in the last video. Well, if we do this, if we take the derivative of e to the f of x, we leave it alone by the product rule for the first term. We take the derivative of it here, so this is going to have to be multiplied here, but then that piece, that p of x, must be the derivative of f of x. That was all explained in the last video. Well, what that means, in order to find the f of x, we've got to undo this as if that is the derivative. It means we've got to integrate it. So this would be the integral of 3x squared over x squared plus 1 dx. And this is where we're going to spend most of our time right now, is just integrating that. And then this thing's going to explode and look crazy, which is why I think it deserves its own video. So let's take a look at how to solve this integral. Let's find that. So I'm going to ignore the e for a second. We'll put it back in just a bit. But let's focus on, you know what I'm going to do? I'm going to leave this. I'm going to put it up here. I'm going to show you 2 ways to look at that integral, and then we'll come back and we'll kind of reevaluate what's going on here. So let's look at this integral of x cubed, 3x cubed, over x squared plus 1 dx. Your first inclination might be to go, oh, wow, that looks just like maybe a trig sub, because we got the x squared plus 1. And it's not partial fractions, because you can't, well, you can maybe write partial fractions, but if you thought about partial fractions, it's not a direct partial fraction because the exponent here is higher than the exponent here. That might lead you down long division. That is an appropriate technique. I'm going to show you that in a minute. But there's also a way around not doing that, not doing long division. Like, I don't like long division. I don't like partial fractions. There's another way to look at it. So I'm going to show you both ways. It's one of the reasons why we're doing the problem right now. What if you just chose to do a substitution? And you go, that doesn't look like a substitution, but maybe we can force it to be. If we did u equals x squared plus 1, you go, let's just run with this. Then du equals 2x dx. You go, I don't see an x. I see an x cubed up there. This is one of the reasons of how I was taught. I was taught how to do integration by substitution, by solving for the dx. And that way, when you put this back, it'll cancel some x's, but some won't cancel, and that's okay. And so I want you to check that out. So if you've never seen that, this is how I would do it in like a Calc 1 class to explain what's exactly going on. And then we sort of transform this into, well, you're really just looking for the dx and all the x's, you group them together. Well, what if that doesn't work? Then you get stuck. Or you have to think about this as 3x squared times x, which is totally fine too. And then you divide by 2, and your x dx, this x dx would change into du over 2, but you'd still have the 3x squared. And we're going to see that on either technique. So whatever you want to do, that's fine. What we're going to do is we're going to look at this as, let's leave that 3x cubed. We know that we call this u, but then we know that dx is substituted, and we use the substitution du over 2x. And this is what I was talking about as far as the canceling is concerned. When we look at this, we know that we could pull out the 3 halves, but x is going to cancel with x cubed and leave you x squared. So whether you write that as 3x squared times x and just substitute, get du over 2, here's our du over 2. It's going to work the same way. So we have a 3 halves integral of x squared over u du. We pull out the 3 halves, cancel one of the x's, we get an x squared over u du. And then you go, wait a minute, that's not how I learned how to do substitutions. That doesn't work. And you go, yeah, you're right. Because all of your variables have to match. And so when this happens, it's okay to use your substitution twice. You might have forgotten about that. It's been a long time for a lot of you since you've even looked at substitution. Some of the comments on the videos are saying, man, I'm so glad you're going through this because I forgot how to do it. It happens to everybody. So whenever you have this situation where you did a substitution, it wasn't trig sub, I don't want to do long division, which you could have, maybe I can just do a substitution and work with it. This happens quite a bit, where if we use the substitution one time to get rid of x squared plus 1, we got that u, maybe we try to use it again to get rid of another variable up there. So if u equals x squared plus 1, and we still have an x squared, well, can you just subtract 1 from both sides and get x squared equals u minus 1? Since that substitution works for u equals x squared plus 1, it has to work for x squared equals u minus 1. It's the same, it's an identity. I mean, you're calling these things equal. So however you add or subtract on both sides, it has to still be equal. That means that x squared, we can rewrite that x squared as u minus 1. Let's take a look at that a little bit closer. So when we have that 3/2 integral of u minus 1 over u, do you remember how when you have a number of terms on a numerator but only one term on the denominator, which is why this works, you can split that fraction up. So we can write u over u, which is 1, minus 1 over u du. And that looks a whole lot better. That's not a fraction. We don't need another substitution. We've split that fraction up into 2 fractions. We don't have any x's. Our u's match our du's. This is something where you can now integrate. So we have the 3/2. Make sure you have parentheses because that's going to distribute here. We have u minus ln absolute value of u. And then we would normally have a plus c, but remember what we're doing. What we're doing is just finding this exponential. We're going to multiply that everywhere. So it's going to get multiplied here, here, and here, and here, which means that that c, that'd be e to the c. Well, that's just a constant, not 0. It's actually positive on all 3 places. So you could easily divide it out. For that reason, we don't do a plus c when we're integrating on top of our exponential. It's not needed. What is needed is for us to put our u back. So we use this to get our u. Okay, now let's use this to get our x's back. So we used u one time to get to x's. We're going to use that substitution again to get back to u's. Sorry, back from u's. So 2 u's. Use the u to get rid of the x's and use the u to get rid of your u's. That's fun. So our u is x squared plus 1. We used it to get rid of our x's, now we're getting it back. And if we distribute that 3/2, notice I'm gonna drop my absolute value because x squared plus 1, it can't be negative with real numbers, so we don't even need that. Now, that looks really nasty. That is just the exponent of what we're going to have to multiply by. So we're going to come back here in just a minute. I'm going to show you how the long division would work, just in case you've forgotten how to do that. And I'll show you that we get exactly the same thing. And whichever technique you would like to use, that's fine. So one more time. What we're looking at is this linear first order differential equation. We put in the right form. We said that's a p, it looks pretty okay. And then we start going, all right, well, if that's our p, we need to integrate this to find the function of x so that when we would take the derivative by the product rule, it would give us that back as that piece, as the chain rule portion of that exponential derivative. We go, all right, well, that's nasty. How do we do it? Not a trig sub. Trust me, you do not want that. I tried it, not fun. So we do maybe a substitution twice, or we look at it and go, that looks like a partial fraction with an irreducible quadratic. Can I maybe do long division? Well, let's try our long division. If we try the long division, remember with long division, you need every power on this numerator in here. Every power of x descending down to a constant. So we'd have 3x cubed, sure, but we'd have 0x squared, 0x, and then a constant of 0. And the reason that is when we start dividing by x squared plus 1, we need some place value holders, because when we start distributing by whatever our result is, then we're going to start multiplying by x squared and by 1. We're going to start getting back some powers of x that aren't x cubed. We're going to get x squareds or x's, and we need to have a place for that. So when we do long division of polynomials, we don't even care about the 1. It just plays along. So we look at What is 3x cubed divided by x squared? 3x cubed divided by x squared, that's x. Sorry, 3x. And when we multiply, we can check the work all the time. Our first terms have to always match up. 3x times x squared is 3x squared. No, it's not. 3x times x squared is 3x cubed, but then when you distribute, so we multiply first term, we multiply second term, notice how we're going to get a 3x. That 3x has to fall under something. If you didn't have that 0x right here, it'd be really awkward. What do I subtract that from? Well, you don't have any x's. This is a way for us to understand that what we're doing here is we're subtracting from something that's not there. We're going to get a negative x. Or if you're subtracting negative, you're going to get a positive x. It just gives your mind a way to see what's going on. So when we subtract, like long division always does, yeah, you need parentheses. 3x cubed minus 3x cubed is 0. 0x squared, there's no other x squareds, that's nothing. You don't even need that. 0x minus 3x. 0x minus 3x. And then you start that algorithm again. Take the first term, divide by the first term, and you go, I can't. Yeah, you're right. As soon as, and this is how partial fractions work, as soon as that numerator has a degree that's less than your denominator, you're done. You can't simplify that anymore. You'd have to use partial fractions or a substitution or break it up like we did here with this fraction. So what to do with that? Well, what to do with this piece of it, by the way, maybe I probably should have done this. We could have pulled that 3 out from the start and not even worried about the 3. Doesn't matter. Not really. You'll see it right now. If we write our quotient, when we divided this polynomial by this polynomial, so when we took this and started doing long division, our result was 3x, cool, and then we had a remainder. And how you write the remainder of any fraction when you're dividing is you can write that remainder over what you just divided by. So this integral changes into that integral. Can you see that if I pulled the 3 out from this term and that term, it'd be exactly the same as if I pulled the 3 out there? Does it matter? Not really. In fact, when we get done with this, we distributed the 3/2 anyway. So take your pick. It doesn't really matter. What does matter is your ability to do the rest of this. So you go, well, this still doesn't look all that great. I can do the integral of this one, but that one looks a little funky. You go, what should I use there? Should I use partial fractions? No, you shouldn't. You should use a substitution, because if you take the derivative of 2x, of x squared plus 1, you're going to get 2x, and all we really care about is the variables matching up. So here, integral of 3x gives us 3x squared over 2. That looks pretty familiar. Then we have this, and we'll see that in just a bit. Then we have this whole, all right, well, if I do a substitution, on just this piece, then we're seeing that this integral is, we had a 3 still. We substitute, I'm using another technique now, x dx. So we have a d over 2, so 3, and then d over 2, 3 over u, d over 2. And if we pull out that 3/2 and integrate, we got 1 over u, that's ln u. And we end up with 3/2 ln x squared plus 1. Let me double check to make sure we're on the right track. Yep. Okay. So you might be noticing a difference here, and you go, well, Leonard, if I take this, I take that, and I take a look at that, and those don't look the same. Even if I distribute this, even I can see that that's got a +3/2, and that one doesn't. What's wrong? What'd you do wrong? Do anything wrong? What happened here is that your your integrals can be off by a constant. We talked about how that constant isn't going to make a difference. So whether you include that or whether you don't, the very first thing you would do is divide it away anyway. So whichever one you have, that's fine. So what I'm going to do is I'm going to use that one. It's a little bit more concise. We can show this one. It's fine, but you'd be dividing anyway. So I'm going to take a break. I'm going to erase the board. I'm going to leave just these two things. So make sure you're okay with your integration. Then we're going to start multiplying back. Let's continue. So now that we found out that that integral is either this or that, and I'm going to show you that both of them work out exactly the same, we can now make that integrating factor. We can now make that rho of x. So we know that this thing that we're multiplying by equals e to the nasty junk, either way you cut it. So I'm going to show this one, and then I'm going to replace a piece of it with this to show you in just a moment that it's going to work out exactly the same. You're going to see what I'm talking about. So let's start with this guy that we got by that long division. We have e to the 3x squared over 2 minus 3/2 ln x squared plus 1. Like, okay, that looks pretty good. Actually, no, it doesn't, but we can still work with it. Let's start separating this and try to get rid of that ln. Remember that what we can do is we can move these exponents to numerators. So we could write this as e to the 3x squared over 2. Well, a couple things. We could do times e to the negative 3/2 ln x squared plus 1. So we're separating. We know that exponents that are added subtracted mean they came from a multiplication. You can choose that as a negative, and then if you added those exponents, you get exact same back. And then we move that to the numerator. So e to the 3x squared over 2 times e to the ln x squared plus 1 to the negative 3/2. I'm just moving that as an exponent. And now we see that's a composition of these inverse functions, and those always eliminate each other. They are inverses. So this is gone. Let's rewrite it just a bit. Now, this is what we're going to multiply to create this result of a product rule. Here, and here, and here. And then I'm going to do what I promised and show you why this difference doesn't matter. So let's go ahead, let's multiply that. So this gets multiplied, man, it's going to be a really long equation here. Here, and here, and here to create this result of a product rule on the left-hand side. Let's do it. dy dx, and we multiply by e to the 3x squared over 2 times x squared plus 1 to the negative 3/2. Yay! And we do it again. So we multiply that here. We still have this garbage. times y. And then we have the equal sign. And we multiply on the right-hand side also. Let's see, it's in all three places. I've got it here, 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 no sign errors. I have the original. Let's make sure that original, that looks pretty good. I will make sure that I have that looking correct. So I used it here. Let's see, make sure I simplified, so I separated that by exponents and multiplication. I know that I can move this as an exponent, so I did that. I know that I have composition of inverse functions, no problem, that's the same. Now we have, okay, that looks really good. So I'm always double checking my work, especially something like this, that's crazy. Now, I mentioned to you that this doesn't really matter so much. So why doesn't that matter? If you took a look at this, and instead of having 3x squared over 2 minus 3 halves ln, and you just had that plus 3 halves, that would have been, please check this out, don't miss this, that would have been here, that would have been, oh, if I have that plus 3 halves, I could separate that as an e to the 3 halves. That plus 3 halves right here, that right there, would have been written as e to the 3 halves. Think about that. This is all going to be an exponent on e, on the exponential. So e to the 3 halves x squared times e to the 3 halves times e to the negative 3 halves ln x squared plus 1. You do the same thing with this one, same thing as that one as you did over there. But that guy, that's e to the 3 halves. So what would happen? Well, when you do this and you simplify this down, you'd still have this e to the 3 halves just floating out there. Well, when you multiply that, you'd have a times e to the 3 halves, and a times e to the 3 halves, and a times e to the 3 halves. And if you have something, this positive number, verify it's positive, it's not a whole number, but it's a positive number that you could factor out and divide. You're not dividing by 0. What that means is that that's an arbitrary constant. It's literally arbitrary. It makes no difference in this problem whatsoever. In fact, if you just divide all 3 terms by that constant, it remains exactly the same. So sometimes you get that. When you're doing these integrals 2 different ways, you might get this awkward constant up there that doesn't make a bit of difference in your integrating factor. You just divide it away, and that's fine. If you were thinking about this like, well, wait a minute, what about if you were just doing a regular integral? Well, that wouldn't make so much of a difference either. You'd have a constant in there that doesn't really matter as far as the adding, subtracting. You'd be able to rationalize that, divide that away. So when we get back to our work, whether you have that plus 3 halves or whether you don't, not such a big concern. What is a concern now is making sure that this is the result of a product rule. You go, that's going to be hard to check. Yes, it might be, because here's the factor that you would have to take the derivative of in order to get this whole entire piece. That means that you have a product rule. That means that you have a chain rule. You start looking, and then you'd have to divide that away. You'd have to factor that out because of that product rule. So let's just imagine that is true. Hopefully that's true. Or you'd have to check it by hand. What we do after we check it is we go, okay, if this is the result of a product rule, this thing that's been added, then this is a factor that we didn't take a derivative of, and this is a factor that we didn't take a derivative of, and they're added together. So remember how we leave the first factor alone, derivative of the second, so derivative of y, that's derivative of y, plus the derivative of the first, that's the derivative of that factor, that's the derivative of that thing, and then times, we leave the second one alone. What that means is that this is a product rule, the result of a product rule, where our product is that. This is the product rule from that thing. On the right-hand side, let's simplify as much as we can. So we know that e to the negative 3/2 x squared times e to the 3/2 x squared. You're multiplying common bases, you add exponents, these things are gone. Thank goodness, right? We'd still have a 6x. Here we have x squared plus 1 to the negative 3/2. That means that when we move this to a denominator, that'd be x squared plus 1 to the positive 3/2. Let's combine them. You've got 2/2 plus 3/2, that's 5/2. So now we're left with this idea of this is a derivative, this side's a derivative of this, and if we want to get rid of a derivative, we know that we can integrate. So let's integrate both sides with respect to x. This was a derivative with respect to x. This, let's find the integral with respect to x. What you do to one side, you have to do to the other. So on the left-hand side, the fundamental theorem of calculus says integrals undo derivatives, basically. So gone, we'd have this e to the 3x squared over 2, and then this x, sorry, you know what, I forgot something. You should have been screaming at me through the video. I told you that this was a product, and then I never actually put the product, so you need a y. Hopefully you caught that. So this is the result of this product rule. Derivative of the first, boom. Sorry, leave the first alone, derivative of the second, plus the first, derivative of the first times the second. Let me say that again because it sounded kind of convoluted in my head, probably to you too. This is the result of this now product with you when you have the y. Leave the first one alone, derivative of the second factor, plus the derivative of the first factor, all that stuff times the second. I forgot the y the first time. So when we integrate both sides, no problem. We have e to the 3x over 2, this x squared plus 1 to the negative 3/2 times y. On the right-hand side, we have another integral. This one's not so bad. It's just a substitution. So when we substitute u equals x squared plus 1, let's do it off to the side here. We'd have, let's pull the 6 out. We'd have 6. We would have x dx is d over 2. So this whole thing is d over 2. And then this is u to the 5/2. So 6 divided by 2, that gives us 3. Let's make that a negative 5/2 so we can work with it. When we integrate, let's see about that. We're going to have a 3, u to the negative 5/2, we're going to add 1, so that's negative 3/2, divide by the new exponent. Threes are gone, move that 2 up, that's negative u to the negative 3/2. And we know what u is. We know that u is x squared plus 1. So this integral equals that thing with x squared plus 1. Let's do that. Now we do need a plus c there. That's important. In fact, this is the first time that we get to look at our initial value. Our initial value says that when we plug in 0 for x, we actually get 1 for y. So let's do that now. There's no ln's or anything in here, so it might be a good idea to do it now. So when we plug in 0 for x, this whole thing would be 0. You would get e to the 0, that gives you 1, times, plug in 0 for x here, that would give you 0 plus 1, 1 to any power is 1. Sorry, times y, well y is equal to 1 when x is 0. On the right-hand side, we have negative 2, of course. We have 0 squared plus 1 is 1, 1 to any power is 1, plus c. This is 1, 1 plus 2 gives you 3, c is 3. Not 1/3 like I did in a few videos ago, just randomly divided for no particular reason, just because I wanted to on accident. So C here is 3. Let's plug that back in. So we're going to have e to that 3x squared over 2. No problem, looking good. X squared plus 1, we can do this. Negative 3 halves y, okay, certainly kind of crazy, equals negative 2 x squared plus 1 to the negative 3 halves, and then we have this plus 3. All we have to do now is solve for y. So we're going to divide both sides by this, which it cannot be 0. So we might think about that as, hey, multiply times x squared plus 1 to the positive 3 halves. That would cancel, x squared plus 1 to the positive 3 halves has to go there. Next thing we're going to do is multiply both sides by e to the negative 3x squared over 2. And that's going to go here and here and here. So we're going to factor it out of the second one. I'm going to show you that right now. So I'm going to erase this. Let's deal with this first. Let's get rid of that. So I'm going to multiply both sides by x squared plus 1 to the positive 3 halves. It's going to cancel, cancel, and go on to that 3. So I still have an e to the 3x squared over 2. I still have my y. We multiplied both sides by this, so this is gone. This is gone. We still have a 2. We have 3 to the x squared plus 1 to the 3 halves. I multiplied both sides by x squared plus 1 to the 3 halves. Now we're going to multiply both sides by e to the negative 3x over 2. And what we're going to do, instead of putting it in both places, we're just going to do this. We're going to say, okay, if you multiply both sides by e to the negative 3x squared over 2, this is going to be gone. So we're just going to get y. But on the right-hand side, let's leave the negative 2, let's leave the plus 3, let's leave the x squared plus 1, let's leave the 3 halves. What we're going to do is just show that this is multiplied by e to the negative 3x squared over 2. And that's about as good as we can get that to look without distributing. So even if you did distribute, you'd refactor it. Man, I hope that made sense. That is just a massive problem. It's like 10 times longer than any of the problems I've seen. So had a special technique in there. It really wrapped a lot of stuff together. Good problem. Hopefully we didn't make any serious error. I know I forgot the y, but hopefully you caught that on your own. And even when you're going through it, you're going to do stuff like that, which is why, if you notice what I'm doing, I'm always double checking my work. I'm always stopping and going, especially without students in here that catch my little mistakes. I'm always looking through, wow, does this make sense? Can I go back? Does this make sense? What am I forgetting? Try that. Try that when you're doing your homework, and especially on your test. If you have that process in your head, you'll make a lot less mistakes. So anyway, special problem. I hope that made sense. I hope that helped you in some way to see what we can and can't do with these things, especially the 2 types of integration techniques we had. All right, guys, I'll see you for the next video when we're going to do a couple applications like with some mixture problems. Have a good day.